My name is Wójcika. Hi everyone. I guess I haven't introduced myself to everyone yet, but I'm a PhD student at Imperial College in London, and I work on numerical modeling of impacts on Mars. And in particular, I'm interested in generation processes of seismic wave from an impact process. And my work is part of the mission Insight, which you can actually see on the picture on the first slide. This is like an artist's interpretation of the lander. And the mission has quite a few components to it, but the one that we are actually most interested in, or the one that I am most interested in, is actually down here. This is the seismic package or size that consists of two seismometers that are on Mars right now, listening for Mars quakes and impacts. And the two main goals of the sort of seismic part of this mission were the sort of primary goals during the nominal mission were to use those seismic signals from quakes and from meteoric impacts to constrain the subsurface of the planet. And also to use the seismic signals from impacts to constrain the impact rate on Mars. So I'm going to start by giving you a bit of a background timeline story to the mission and to my project personally. So you can see a real photo of inside of the lander on the slide now. So this is one of the selfies that the lander took quite early on in the mission. InSight actually landed in 2018 in November in Elysium Planitia. And at that point, the sort of detectability estimates for impacts were predicted to be between a few to tens of impacts per year. And these were based on various scaling laws that used sort of cratering crater size scalings and relating impact energy to different things and predicting how what sort of amplitudes we can expect and how many impacts we can expect to detect seismically. So what you can see in this picture now is the actual part that I pointed out on the previous slide, and this is the seismic package. So inside of this windshield are two seismometers, a short period and a very broadband period, seismometer. And the reason why we needed a windshield, which was deployed in February 2019, so a couple of months after the landing, was because the seismometers are actually sitting on top of the surface of Mars. And so they're quite susceptible to atmospheric noise, so things like wind. And for us to actually be able to listen to sounds of Mars at a better noise floor, we needed this windshield to be on top of the seismometer, the seismic package. So I'm going to fast forward a little bit to end of September 2019. So InSight has been on Mars a couple of months. It's been listening to at this sort of improved noise floor for a couple of months now, and it's recorded 174 events, or Mars quakes as we call them, and 20 of those had moment magnitude 3 to 4, which are still pretty much the highest, or some of the highest magnitudes or amplitudes that we've seen on Mars. At this point, we haven't actually detected any impacts. We were sort of disappointed, but it wasn't super unexpected because we thought, well, worst case scenario, we'll get one or two maybe in the whole span of the mission. So we kept waiting. So unfortunately, fast forward till now, we actually have more than 500 Mars quakes recorded and still no impacts that have been actually recognized in the seismic data. So at this point, you might be wondering, well, why do we actually care about impacts on Mars or their seismic signature if we're not detecting them? Then we're not detecting them. Well, there are a couple of reasons why we might be interested in that. So first of all, impact craters can actually be detected in two ways. And the way we've been doing it in the past is using orbital imagery. So we've been photographing surfaces of planetary bodies, and we've been looking for craters that have been formed since we last photographed this area. But the secondary way that we can detect impacts and actually constrain the impact rate is using seismic signals. And especially for a project like InSight, this can give us a very well-constrained location, which is something that's quite tricky for a seismic event when you've only got single station project, because you can't really do triangulation. You can't really compare signals from different points on the planet. You only have this one signal that you've detected. You have no idea where it came from. So constraining the location would be very, very useful. What you could also do is get a secondary estimate of the magnitude based on the crater properties. So if you had a crater that you detected using imagery and you could match that to a seismic signal, then you could compare the properties of the crater and, ultimately the properties of the impacts that actually produced it, and compare that to the magnitude or the amplitude of the waves or the magnitude of the event itself. And of course, like I said, one of the main goals of the mission was to help constrain the impact rate on Mars in a sort of secondary way to orbital imagery, which is very important for things like dating planetary surfaces. Now, my work is focusing on this point 3 on the slide, so getting a sort of secondary estimate of the magnitude and actually relating the crater or impact properties to the seismic signal properties or the properties of the wave that's actually been generated during the impact. So the sort of overarching question for my project is, why are we not detecting impact? Or at least now it is. It wasn't when I started my PhD, but now we're actually wondering why we haven't detected any. So, there are many reasons why that could be happening, but you could summarize them in sort of 3 main themes, if you'd like. So first of all, you could say, well, impacts maybe are just not happening on Mars, and we're not seeing them because they're just fewer in number, and they're happening less than we thought. So therefore, we're not detecting them seismically because we're just not having impacts happen. Well, that could be true. And like I said, one of the goals was to constrain the impact rate. So that could still partially be true. But I want to point you to this paper, Delaware et al. 2020, where we actually detected a fresh crater that was very, very tiny. It was 1.5 meters in diameter, but it happened 37 kilometers away from the InSight lander. Now, statistically, that's very, very lucky. So, there are craters happening on Mars, and we know that they are happening. We are still detecting them using imagery. I guess the overarching problem with that is that it's very hard to constrain the timing of these impacts. So we're not often taking pictures of the same area in this span of maybe a couple of years. And of course, InSight has only been on the surface of Mars for just over 2 years now. So that could be one of the reasons. Well, second of all, seismic impacts could just be less seismically detectable. So they could be producing seismic waves which are smaller in amplitude. So the sort of magnitude of the quake that's actually being produced is smaller. Therefore, we're not detecting them because they're not above the noise floor. And the third reason could be that signals from impacts are actually not that easily distinguishable from Mars quakes. So maybe they are in our data, but we're just not realizing that they're there, and we're not recognizing their properties. And in this talk, and in most of my work, I focus on those 2 final points, looking at impact detectability. And I'm starting to look at what the properties of the source actually mean for the signal that is detected at the receiver. So the approach we've taken is numerical modeling or forward modeling, and we chose to simulate a suite of vertical impact scenarios that would form craters between 1 and 30 meters in diameter. And this was chosen to be craters that are big enough to be detected from orbit, so that we could actually see them and confirm that they exist. But craters that are not so big that they're very unlikely to happen in the mission's sort of lifespan. So 30 meters was sort of the limit for that. And these point to impactor radii of between 3 and 50 centimeters. And it turns out that these impactor sizes actually are very susceptible to deceleration in the atmosphere. And so if you start with a 10 kilometers a second atmospheric entry velocity at 45 degrees, you actually end up with very low impact speeds of between 1 and 6 kilometers a second. And this table is showing you all of the scenarios that we looked at. So we use ISAIL 2D shock physics code to model this process. So we set up our simulation mesh, which is a typical mesh was about 3,000 cells by 3,000 cells. And it looks something like this, where we just have a mesh of cells, a mesh for the impactor, and then we fill it with materials. And then we let it run for a little bit. And then we track the wave until the edge of the mesh. What you can see in the slide are 3 snapshots of one of our simulations. So this particular example is for a 1 kilogram impactor that strikes the surface at about 2 kilometers a second. And in the first snapshot, you can see the shock wave that has just been formed. It's still very, very much near the crater. And the crater is still very much in its early stages of being formed. In the second snapshot, you can see the wave has moved a little bit away from the crater. It's still a plastic wave, so it's still losing a lot of energy on the forming and breaking the target material. And then as we track it all the way to the edge of the mesh, which is what you can see in the third, the snapshot here, that wave will actually decay into an elastic pressure wave, which then has its properties fairly constant, and that's what will propagate far field to our receiver. In terms of material models, we use a 44% porous basaltic regolith for the sort of upper tens of meters of Mars. And you can also see the black dots in this slide that actually represent Lagrangian probes. So our entire simulation is Eulerian, and that means that we have our mesh in a constant place and we let the material flow through the mesh and move quite freely. But the Lagrangian probes actually act as almost virtual seismometers, so they allow us to track sort of properties of the response of the particular packet of material as a function of time. So one of the first concepts that I wanted to talk about today was the concept of seismic efficiency. And seismic efficiency is the portion of impact energy that's converted to seismic energy. So that's how much of the energy actually ends up not being deposited in the crater formation, not being used in deforming the target under the crater, not being used in ejecta, not being used as heat, but that's the energy that actually ends up in the wave that propagates far field. And the way we do that, the way we calculate it from our simulation is using these Lagrangian probes that I just mentioned, which allow us to track the pressure wave or the pressure pulse that travels across the mesh. So you can see the 3 pressure pulses here that corresponds to these 3 probes. And what we do is we measure the width, or the half width of each of these pulses, and then the peak pressure, and we approximate it as a triangular pulse, and then we use this equation here to calculate the energy in that pulse effectively. And we do that for every single probe. And when you actually combine these, what you see is that when you're very much near the crater, so between 2 and 4 meters, your wave is still losing energy on that deformation, or because it's a placid wave. But as soon as you get to like 9 or 10 meters away, your wave stops losing energy on that, because it becomes elastic. And so that's where you can actually measure the seismic efficiency, because that's the sort of intrinsic energy in the seismic wave. So we do that calculation for every single one of the 13 impact scenarios that I showed you before, and our results show that seismic efficiency is between 10 to the minus 6 and 10 to the minus 7, which you might think that's quite low as a portion of the energy that actually ends up being in the seismic wave. And yes, that is quite low, even as far as other studies go. So in this plot here, there's quite a lot of points, there's quite a lot of data here, but seismic efficiency is actually one of the least well-constrained parameters in the impact world. It varies between 10 to the minus 2 all the way down to 10 to the minus 6, or 10 to the minus 7 in our case. And our results fall on the very bottom of that scale. And on the x-axis, you can see the energy of the impact. But you could argue that there is a slight sort of decreasing trend with impact energy, but there isn't really a rule of thumb to calculate seismic efficiency, and it's very much susceptible to different material properties. So some of these points are numerical models, some of these are lab experiments, and I've also plotted the missile impacts and the Apollo man-made impacts on the moon. So when that's where the booster, the sort of lunar module and the booster engines were actually dropped onto the moon in a sort of controlled impact experiment, and they were recorded by the lunar seismic network. So what I want you to take away from this plot is that there's a very big range of values for seismic efficiency. But I've also plotted the value that's accepted for InSight, or that was accepted for InSight in those pre-landing estimates that were then used to calculate the estimates of the number of impacts that we might detect with InSight during its lifetime. And that value is this horizontal line here, which is at 5 times 10 to the minus 4, which is 2 orders of magnitude bigger than what our simulations show. And so the sort of a simple conclusion from that is that points to a lower detectability of impacts on Mars based on the seismic efficiency. The second sort of chunk of results, or the second piece of information that we investigated in the study was looking at seismic moment, or I should say seismic scalar moment. But I don't know if we have any seismologists. I'm not a seismologist, so I don't think we do. So I guess I should explain what seismic moment is. Seismic moment is inherently a tensor that describes the seismic source geometry and its magnitude. And so in this case, I'm focusing on the magnitude of it, not the actual tensor itself, but just the magnitude. But that's seismic moment tensor is actually being used on Earth, at least, to define the earthquake magnitude scales. So when you hear, earthquake of magnitude 5 stroke strikes, it's wherever, this is based on the seismic moment value. That was calculated for the seismic waves. what's interesting is the seismic moment is actually used in the wave propagation modeling to predict far-field ground motion. So you can pass to a piece of code, seismic moment tensor, or its magnitude and shape, and you can basically propagate a wave and get out a modeled waveform that you would get at a receiver far away on the other side of the planet. So we use 3 different methods to calculate seismic moment as a function of radius from impact. I'm not going to go into too much detail on how we calculate it. It's a bit of a similar process to what we did with seismic efficiency. But what you can see immediately is that these plots look very similar to the seismic efficiency plots. And so what that basically means is that as the wave moves away from the equator and it becomes elastic, your seismic moment should become a constant, at least until it reflects off the boundary of the simulation. And the good news is, what you can see on this plot is that either 3 methods agree to within a factor of 2, let's say. So, like I said, we've got 3 methods for each scenario, and then when we plot these all together, we find that seismic moment scales almost linearly with impact and momentum. And we also derive a least squares scaling relationship that's plotted here as the dashed line. We might be wondering, okay, well, what does that actually tell us about predictability or anything useful for insight? Well, we can actually combine these results with the seismic efficiency results and plot our seismic moment values against seismic energy. And on this plot here, you can see all of these colored points are data from earthquakes, from some explosions. And on top of that, you can see the dashed line is the scaling law from Timmy and Wójcika 2011, which is one of the scaling laws that was used again in those pre-landing estimates. So you can see that our results follow, which are, so my results plotted all the way down here, and there are these hollow points. And if you zoomed in to this region here, in that space, our simulations actually predict a lower seismic moment for a given seismic energy. So they don't quite agree with these previous scaling relations. Now, if we combine that with the crater size estimates that we have for our simulations, and we zoom in to the right sort of crater diameter range, and we plot all of the other scaling relations that are available, then we can see that the ICL simulations actually show us, actually predict seismic moments that are between 40 and 60 times lower than the previous scaling relationships suggest. Now, in short, what that tells you is that predictability of impacts is lower than we previously thought, because simply the magnitude for a given crater size of a quake that's produced is going to be smaller. So the impact is not going to be as detectable as we expected it to be. To tackle this problem from a bit of a different side, you can also look at seismic data from some of the known impacts. So you can look at data from the lunar impacts that I mentioned, the sort of artificial lunar module and the Saturn booster engines. And you can also look at some of the missile data from Earth that were carried out in the US. And there are different ways you can scale the P wave amplitudes that were recorded by these. And you can use energy, which is what has been used in the past. So this is the energy scaling based peak wave amplitude as a function of distance away from the source for a range of different crater diameters. So, for example, if you were to look at the crater diameter with crater, a 10-meter crater, and you stood 10 kilometers away, you would be well above the noise, which is marked by these shadings. And if you were to go all the way to 1,000 kilometers, you would be in the sort of gray area where you might detect it in during low noise, but not in high noise, and so on. And so you can use these scalings to predict what the peak P wave amplitude for a given crater would be, and then see which craters and how far away they could be expected to be detected by InSight. So yeah, I should have mentioned that the noise levels on this figure are actually based on the landing site InSight, so the real noise levels that have been measured. So yeah, the top one is the high noise and the low one is the low noise, depending on the time of day that you look at. So, however, like I said, seismic efficiency is incredibly uncertain, and you've seen that there are many orders of magnitude of different estimates, and we've seen that seismic moment is very nicely linearly dependent on momentum, and if peak wave amplitude is something that scales with seismic moment, which it should, because they're sort of proportional, then maybe impact momentum is something to consider more in these scalings. And also, there's the fact that we still have no impact detections, which means that most of these scaling relations that we used in the past should be revised, at least to some extent. So what we can do is we can modify this approach to rely on purely momentum-based scaling laws. And what you end up with is something that looks like this. So the left-hand side panel is the exact same plot that you've seen on the previous slide. And the two other panels are the two momentum scaling versions. So depending on whether you use the lunar data, so these impacts were into sort of cohesionness, more sandy target properties areas, or if you use the terrestrial missile impacts, which were into more cohesive soils, and you use these different properties to scale your crater sizes, and you use these different data sets to scale the actual data, then you end up with slightly different versions of the same scaling. Now, the reason I've highlighted this 10-meter crater in red is because, of course, it moves across the different panels, but it doesn't move as much as the other lines. And so I'm sort of using that as sort of reference point so that you can quite easily see what actually happened to the lines and what that actually means. What you can see is that the lines have pretty much got more spread out in the momentum scaling plots. And what you can immediately see is if you look at the lines that are below 10 meters, so craters that are smaller than 10 meters, they've moved down. So that means that these craters or these impacts that form those craters are actually less detectable because they produce lower amplitude waves. On the other hand, if you look at the lines that are above 10 meters, they've actually moved up. So they are more detectable than previously expected. Now, what that means is that the best chance of detection is a crater that's larger than 10 meters that's actually formed within a couple of hundred of kilometers of Lander, and not a very small crater that's very much more likely to happen. So you wouldn't necessarily be able to detect something that's only a couple of meters wide. So again, that could partially explain the lack of detections of impacts to date. Now, the last two we've come full circle, the last sort of piece of information that I wanted to talk about is something called seismic source time function, which is going to help us look at this problem from the other side. So looking at this last point in one of my initial slides, where I said that the possible reason for the lack of detections could be that the signals from quakes and impacts are actually not that easily distinguishable. So seismic source time function is something that I've recently started working on, and it describes the vertical force that's applied to the target during the impact as a function of time. And the shape of that source time function is going to, at least in part, define what the frequency content of the signal that's detected at the receiver is going to look like, or what the waveform is going to look like. And so we can calculate the equivalent seismic force from our simulations. And that's what you're seeing for that same model that I've shown as an example throughout the presentation. That's what you can see in the figure as the solid black line. That's the numerically calculated source time function. But what we really want to do is we want to approximate this source time function with something that's mathematical, with something that's easily generalized, and with something that we can apply to different impact scenarios that we haven't necessarily modeled. And so what we do is we use this Jeffreys pulse equation, which relates, so the Jeffreys pulse equation basically, the Jeffreys pulse basically looks like the dashed line here. And the equation for it is this thing. And it basically relates the force to time, obviously. But this PI here is the impact momentum, which we can easily calculate for a scenario that we're interested in. And then this mathematical constant alpha. Now, alpha is not a physical thing. It's not a physical quantity. It's not something that we can measure for an impact that we want to consider. So what we do instead is we find an optimal alpha for each of the models that we've simulated, and we try and relate that back to some sort of combination of physical parameters of the impact. For example, what we end up with is this TC characteristic timescale, which we define as the time taken for the shock wave that's generated right at the start of our simulation to travel twice the impacted diameter. And that seems to work quite well for fitting alpha. Of course, we can improve on that relationship once we add more different material parameters, more different sort of a wider range of initial impact properties to this study. But what we can do is we can then find a sort of mathematical relationship between the two values, which is shown as this line here. And then we can plug it into that equation that I've shown on the previous slide. And that then gives us a means of calculating seismic source time function for any impact that we haven't necessarily simulated. And then that, in turn, will lead us to characterizing the signal of the receiver, because this is going to be related to the frequency content and the waveform and the sort of peak or corner frequency of impacts. And maybe this will tell us something about whether there are any impacts hiding in the inside data or not. Okay, so that was a lot of information, I can imagine. So just a few key points to finish off on. Constraining seismic properties of meteor impacts is very important for planetary exploration, for dating planetary surfaces, for constraining impact rates, and for constraining subsurface properties of planetary bodies. Our simulations suggest so far that impacts are less seismically detectable than we thought, and that's the case at least for Mars. And current work involves constraining how such a signal would actually look at the location of the receiver. And I'm just going to leave you with this slide where, if you're interested, you can jump to my paper on the seismic moment efficiency. And I also had an abstract and a presentation at LPSC this year on seismic source and function and frequency content. And we also recently wrote a very interesting paper on trying to constrain whether we could detect the landing of the Mars 2020 mission on Mars with our seismometer at InSight.